Hi, this is Mr. Anderson, and today I'm going to be talking about Newton's three laws of motion, and today's a perfect day to talk about that, because when it starts to snow and the roads get icy, you really start to understand how objects are affected by Newton's three laws of motion. So I hope you enjoy. Some would argue that the greatest scientist of all time is this guy, Sir Isaac Newton. He was clearly a genius. He summarized all of his decades of work in the Principia, which some would argue is probably the greatest book, scientific book ever written. It kickstarted physics. In fact, it is. Most of the formulas in a typical physics book come right out of this. He also explained gravity and how universal gravitation worked, and then quantified the movement of the planets and summarized the work of Kepler. You're maybe familiar with the story of that somehow an apple fell out of a tree and hit him on the head. That's probably not a true story. That didn't somehow bring about his genius, but he definitely referenced that in some of his work. And so let's go through Newton's laws of motion. First law is sometimes referred to as the law of inertia. It reads this way: every body remains in a state of rest or uniform motion unless acted on by an external unbalanced force. This kind of summarizes the work of Galileo. What it means is that all objects that are at rest or in motion have a certain amount of inertia, and that never changes. And so let me give you an example of that. Let's say I were to make a magical apple and then let go of the apple. The apple would fall down. And the reason why is gravity is pulling it towards the earth. And so it's hard to see Newton's laws of motion with gravity and friction and air resistance kind of at play. And so I'm going to use my imagination to get rid of gravity and friction and air resistance. And so now I have a magical place where we can study Newton's laws of motion. So let me make that apple again. Okay, so now I've got an apple. And if I let go of the apple, it will just sit there. And the reason it just sits there is because Newton's first law of motion. It's an object at rest, and so it will remain at rest. Now, it'll remain at rest until it's acted on by an external unbalanced force. What does that mean? Well, I could push on that apple from both sides. As long as I'm pushing on it with the same force from either side, it'll remain there as well. If I apply an unequal force, let me try an unequal force to the apple, then it'll start to spin, and the reason why is I've applied a unbalanced force. So let's bring gravity back for a second and get rid of that apple. Now, that's only one part of it, that an object at rest remains at rest. Let me take another apple, and this one I'm going to give a little push, and that apple will move off the screen. And the reason why is it's an object in motion, and it will remain in motion. And so that apple, that virtual apple, it's just going and going and going, and it'll go on forever, according to Newton's first law of motion. And so again, if you're at rest, you'll remain at rest. If you're in motion, you'll remain at motion unless you get acted on by an unbalanced force. And that's Newton's first law of motion. Where have you experienced this before? Great example would be the toilet paper example I give. If you want to get paper off of a toilet paper roll, but you can only use one hand, you can use the law of inertia. If you were to somehow pull the toilet paper very slowly, it's not going to help you. And that's because there's a lot of friction. But what you can do is you can grab a little bit of toilet paper, and if you quickly move, the inertia of the toilet paper roll will hold it in place, and you can get some of that toilet paper off. So that's Newton's first law of motion. Let's go to Newton's second law of motion. Newton's second law of motion is arguably the most important of the laws. And the reason why is that we get a number of formulas that come off of that we can use to actually measure how objects move. So what is it? The acceleration of object is directly proportional to the force acting on it and inversely proportional to its mass. So what does that mean? Well, the best way to remember the second law of motion is this equation up here, where force is equal to mass times acceleration. So let's make a mass for a second. So I'm going to make a weight, like that. Okay, so now we've got a weight here. And so I can apply a force to a weight. And so let me apply a force to a weight from this side, and I can make that weight accelerate. Now let's make a weight that's a little bit larger. So if I make a weight that's a little bit larger, and now I apply that same force to it, it doesn't accelerate as quickly. And the reason why is that if I have a bigger mass and I apply the same force to it, I'm going to get a slower amount of acceleration. And so we can use that equation to actually do some calculations, and I'll do that in a separate podcast. Know this, that if I apply a force in this direction, that's a vector, it's in a direction, it's a magnitude in a direction, I'm going to get that acceleration in the same location. So I could keep, for example, my mass the same. So if I keep the mass the same of a weight, and now I apply a greater force to it, I'm going to get a much greater acceleration. So that's Newton's second law of motion. Let's go to Newton's third law of motion. Newton's third law is sometimes referred to as the law of action-reaction pairs. For every action, there is an opposite and equal, or equal and opposite reaction. What does that mean? Well, when I push on something, like if I were to push against a wall, not only am I pushing against a wall, but the wall is pushing back at me. Now you might think that's kind of silly, but try pushing against a wall when you're sitting on a skateboard, and you'll find that when you push in that direction, the wall is going to push you equally in the opposite direction. Where is this important in Newtonian physics? Well, rockets use this to launch themselves. And so let me make a rocket, for example. So I've made a rocket right here, and let me turn it in this direction. So we don't have gravity, and I'm going to let it go and just let it hover there. Now, in order for a rocket to work, the way that works is that I can apply a force in this direction. So that's the fuel that's coming out of a rocket when you actually launch it. And then, so that'd be an action or a force in this direction, and I'm going to get an equal force in the opposite direction. And so if I apply a force by lighting that rocket, it's going to shoot out jet fuel in this direction, and we're going to get a reaction in the opposite direction. So let's try that. So that's Newton's third law of motion. Remember, for every action, there's an opposite and equal reaction. And so that's Newton's laws of motion. They essentially govern the way objects move, but you can't always see it. And the reason why is that friction tends to get in the way. And so if you can get rid of friction, you can let Newton take over and sit back. I hope that's helpful.